Next, we got Zack from this place where he works, and he's going to be talking about things and malware and creating it for good things, I guess. So,
awesome. Thank you. How's my volume doing? Good? Sweet. All right, so today I'm going to talk about analyzing malware by creating it. So we're going to go through some kind of simple toy examples. We're not going to drop anything truly novel here today. There are some code samples here in the talk, so if your eyesight isn't great, it may be beneficial to move forward just a little bit, but no judgments if you want to sit in the back. So a little bit about me. I work at Red Canary as a threat hunter, so I help handle incidents and hunt threats and analyze malware. I also have an undying love for pizza, and this is not a photo of me, but I do have the same jacket. Show of hands, how many people understand this jacket reference? Not as many as I'd hoped for. Cool. So this is kind of the thesis statement of this talk, is when you're starting your malware analysis journey, starting with obfuscated code is just objectively wrong, right? It is a very deep rabbit hole. There's a lot that you need to understand. And by approaching the topic from a slightly different angle, you'll realize that malware is simply software, just with a specific purpose in mind. And the engineering decisions that malware authors make will really help you make more sense of your analysis as you're going through this process. And it'll make things a little bit more clear. So just an overview of what we're going to talk about. We'll talk about how malware fits into the puzzle of an intrusion, as well as some high-level analysis concepts, like how to think about analyzing or reverse engineering code, and then some script-based malware examples, and finally, we'll wrap it up with some binary malware. But first, let's talk about why adversaries use malware at all. They really don't need to. You think about something like a business email compromise scenario, right? There's no need for an adversary to leverage malware there. They simply have credentials that they can use to target your organization and trick people into sending them gift cards and money. But malware does provide additional functionality in order to achieve their end goal or purpose. So that's kind of why you start seeing the introduction of malware into intrusion chains. The adversary is also thinking about things like how they can remain stealthy. Sure, there's living off the land techniques that you can use of those binaries that are built into Windows. A famous quote from Tim Malcolm-Better is that in the age of EDR, spawning processes are expensive, right? So every time you create a new process, if you're using a living off the land technique, you have to provide it certain command line arguments. They're going to give away what it is that you're trying to do as an adversary. And there's also some purpose-based things that malware just needs to build that custom functionality to perform. So for example, as an adversary, how would you provide OBSEC-safe, enterprise-wide encryption of endpoints without compromising that key? There just genuinely isn't that functionality built into normal operating systems, so you kind of have to come up with your own custom implementation. So let's jump into some high-level analysis concepts. When you're getting into reverse engineering malware, you truly need to understand what your end goal is. It can be a very deep, windy path. The rabbit hole is infinite. So you really need to know what your goal is, like what the thing is that you're working towards. Do you truly need to understand how that unpacking routine works? Or are you simply interested in just extracting those indicators of compromise that you can use to hunt in your environment? Another really important concept is called backtracing. Sometimes you'll hear this referred to as bottom up. A lot of people, when they start reverse engineering malware, they'll start from line one and they'll work their way down. However, due to things like obfuscation and adversaries intentionally trying to make your life difficult, they will make that not a very effective strategy. So backtracing or starting at the bottom is a more effective approach. So start at that interesting piece of code, look at those parameters or arguments to that function, and work backwards. Find out where that information came from and how it's being used in that function call is oftentimes much more effective than trying to read from the top to bottom. One of the fundamental problems in computer science is what is data and what is code. For example, if I give you a series of 8 digits, 90909090, what does that mean? Depending on the context of how we interpret that data, it changes its meaning. If I'm giving you a decimal number, that's a large decimal number. If I'm giving you hex values, that could be 4 capital Z's. Or if it's a CPU instruction, I could have just given you 4 no-op CPU instructions. So a lot of what malware is doing is it takes this block of data and it interprets it in a specific way that provides the computer instructions. Because of that, there are some things that just can't be obfuscated. You always have to have that initial loader stub or that initial starting point of the code that the computer understands. And from there, it can go on and it can do some of that more complex obfuscation or deobfuscation at runtime. So understanding that no matter how crazy the malware sample is, doesn't matter if you're analyzing the next Stuxnet, at some point, there's some part of the code that is totally, perfectly understandable to humans and computers. So let's go ahead and jump into some script-based malware. Some of the really common ones that you'll run across are shell scripts. Things like LNK files, BAT files, or PowerShell. You'll notice that PowerShell has that little asterisk next to it because that can get quite complicated. Talk about it later. But shell scripts are essentially your command executors. So it literally just runs the commands that you put in the script. It's a plain text file. It's quite simple, not overly complicated. And then you have Windows script host files. These are things like your HTA files, your JS files, your VBS files that are essentially containers for JScript or VBScript code. And then finally there, we have macros. Macros are written in a programming language called VBA, or Visual Basic for Applications. And really kind of the killer feature there is that it can interact directly with the Windows API. We'll talk more about those later, but seeing less and less macros there. So let's talk about LNKs. These are basically the shortcut files that you're going to see on your desktop. They're very simple. If you wanted to create your own LNK file, you can do so on the system. And then to get it to do malicious things, you just have to right-click on it, go to Properties, paste in your malicious command. Very trivial to create. Bonus points if you go out of your way to change that default icon. So it tricks the user into looking at that icon and thinking, oh, this is a PDF, rather than, oh, this is malware. However, the icon isn't embedded in the LNK file itself, so you have to find a steady place on that host or victim operating system that you can pull that icon file from. So here's just a quick demo of what that looks like. So here you see my command in that notepad window. I'm going to create a new shortcut. I'm just going to paste in that command right in there. This is just a boring interpreter reverse shell, or it could be a boring interpreter reverse shell. Give it a name called fun, and then we right-click on it and go to properties. So inside of properties, we can go ahead and quickly change that icon, give it a something with a little bit more flair, like maybe this icon that I just downloaded. And go ahead and hit apply, and you'll see that the icon is updated on the desktop. All we have to do to execute it is just double click, and now we see our good friend Rick. So one of the things that's important to think about there is that's what you can do as an adversary to create that payload. Think about those certain constraints that the adversary is under. Like, for example, the icon needs to be embedded on that host operating system at a predictable location. And from there, you can start to wrap your head around the engineering decisions they make about using the icons that are embedded in Edge, for example, to make that PDF, because they know it's going to be on every system. So here's an example of what an LNK looks like abused in the wild. And here's that eye chart for those of you in the back. To get to this point, I essentially just downloaded a malicious LNK file from Malware Bazaar. This one happens to be Remcoast Rat, and ran strings against it. Once you run strings against it, you're pulling out those ASCII readable strings. So kind of like what we talked about earlier is that you don't have to understand all of this, right? So if you just start scanning it from top down, start looking for some of those things that you might be able to understand as a human being. And if we do that, we'll see this red block highlighted here. You see that string that kind of looks like a URL. You see a reference to an environment variable that's referencing app data. And then also down here, you'll see the word wget. So wget is just a PowerShell alias for invoke web request. So it grabs a resource from the internet. And then from there, it's writing it out to a file. So everything up top is literally just obfuscation and weird stuff that you don't necessarily need to understand that winds up being, here's your source. That's just the sink for this variable at wget. So one way to kind of make that analysis process easier without having to understand particularly how that deobfuscation routine works is you can just copy and paste that PowerShell script into PowerShell ISE, so you have that nice graphic interface. And then at the bottom, rather than writing that out to a file and executing it like we see in the example to the left, what we can do is we can just pipe it to write host. So just output that URL that it's going to retrieve the malicious payload from out to the command line, just echoing it out there. So here, for example, this is basically just using an LNK file to use PowerShell to reach out to the internet to download example.hta, write it to the host, and execute. Speaking of HTAs, HTAs stands for an HTML application. It's basically a container for JScript or VBScript code, but it also contains HTML elements as well, so you can kind of customize that view that's presented to the user. You can kind of think of it as a rudimentary Electron app without that host-based sandboxing. So those commands that are running are truly running on the host and not inside some type of Chrome isolated sandbox. One of the features of JScript and VBScript that we see abused over and over and over again are these wscript.shell objects. So I would definitely emphasize the importance of focusing on those first. So here's what a trivial example would look like if we were starting to design this malware from scratch. You have essentially your script language, so you're telling it whether you want VBScript, JScript, etc. Creating this new ActiveX object, wscript shell. You have a command, and then you give it that run, invoke that run method with that command that you want it to run. So it's a very simple, trivial example just to demonstrate how adversaries start to build out their payload. And it winds up looking something like this. So if the user double clicks it, you'll get this annoying window that's kind of like a mini web browser, and then you'll also get our calculator popped. So how would adversaries take this and improve on, right? So this is obviously a bunch of garbage. This is not something that an adversary wants to run in their target environment. It's not something a red teamer wants to run. How can we iterate on this and improve it a little bit more? So what we can do is we can start to obfuscate some of those strings. So here you'll see with our shell object, we're creating a string from character codes. Similar to what I talked about earlier with that example of the 90 digits being a capital Z, these are essentially ASCII values that represent wscript.shell. So what we can do when we create our ActiveX object, we can just pass in that shell object variable that's constructed from those individual hex values. So then if you're looking at the strings of the file itself, you won't necessarily see that wscript shell object. But if you work backwards from the ActiveX object that's created, you find it. And then we do the same thing with our command, and then we're passing it to that run. The final line that you'll see there is window.close. So we had that annoying window. Let's just automatically close that, so then the user is not truly aware of what's happening. So one really useful exercise that I've found is looking at different red team frameworks that are out there and think about how do they code their droppers for HTA files, etc. So you'll see a lot of references in this talk to Metasploit. It's a very well-known framework, and the template files are all open source like this. You'll see that they handle some of those same obstacles in slightly different ways. For example, that very second line of code, you'll see that they're actually moving that window out of view of the user rather than just focusing on closing it when it's complete. So then that way it isn't on the screen for even a fraction of a second, because the first thing that script is going to do is move it out of view. And then you see that it's creating that WScript shell object. It's also using an additional feature to kind of find the precise location of PowerShell before it goes ahead and uses that var_shell.run method invocation just to launch PowerShell. So here's an example of what this would look like in the wild. So again, another eye chart. This is an example from hcryptcryptor. So this is a malware family that essentially they sell their services as a cryptor for a follow-on payload. So an adversary writes their new information stealer and they want it to evade antivirus. They'll pay hcrypt to essentially create this wrapper that drops the payload onto the system. So again, you see some obfuscation here that makes it hard to understand. But if we focus on our fundamental concepts of, bottom up, let's scan through this list and try to find those things that do make sense to us and work backwards from there. So here we find our create object WScript shell that's assigned to a variable OX. So that tells us, here's our WScript shell object. I would expect to see a .run method invocation. So let's go ahead and read through the code to try to find it. And we see it down here at the bottom. See ox.run, and then it's given the command line OK. So OK is just a concatenation of all of the other strings that you see in the middle there with some other miscellaneous obfuscation built in. But just simply by reading that, we can tell that it's doing something with PowerShell. We have a URL. And if you read it closely, you can see that it's essentially just doing net web client download string from that URL you see there. So now we'll pivot on to macros a little bit. Macros have been fading in popularity ever since Windows kind of made the decision that any Office documents with macros that have been downloaded from the internet shouldn't be able to execute, and making that a default decision. So what we did is we saw a lot of adversaries moving to other execution styles like LNK files. But macro files are written in VBA, and they allow for direct access to the Windows API. That's super powerful because it allows adversaries to do anything that you'd really want to do on the operating system inside of the VBA code. Unlike some of those other things that we saw where you'd have to call that WScript shell object in order to run commands, they can access the Windows API directly. One of the big things that you see over and over again is the use of these auto open functions. So what the auto open functions do is essentially when that Word document is opened up, go ahead and automatically run the malicious payload. So you'll see that over and over and over again. If we focus our attention on the function that's called by that auto open routine, will serve us well. So here's a simple example from Metasploit again. We're seeing that auto open function. And we're also seeing the workbook open. So that this would make it functional in an Excel spreadsheet as well. And then it's simply calling that shell command. So this is a very rudimentary macro. There's a lot more advanced things that you could do there. For example, with Unicorn. So Trusted Sec has this project out there called Unicorn that develops more advanced payloads for macros. Again, if we focus on those fundamental concepts of scanning from the top down, finding those things that we can read, and then working backwards to see those function calls. If we scan our way through, we'll see this create object. We might want to know what type of object it's creating, right? Is this a WScript shell object by chance? And if we follow that argument backwards, we'll see that it is in fact a WScript shell object that's being created. So now that we've confirmed that, we want to look for the invocation of the run method and then see what arguments or commands are passed to it. And we can see that run command way down at the bottom there. The commands that are getting passed in are a little bit complicated for this example, but you can kind of see them at the top there. Helpfully, Unicorn also has some additional code in there to make users a little confused, where it'll pop a nice message box saying that this document is not compatible with this version of Office. So now we'll jump into PowerShell. So PowerShell can be one of those command executors, just like we saw very early on in the slides, but it also has a lot of really advanced functionality built into it. You're going to see a lot of base 64 encoding whenever you're looking at PowerShell, because it handles it really well natively, and it's trivial to deobfuscate. It also does things like saves the user from dealing with white space and like line breaks and things like that, and just encodes everything quite nicely. But you'll also see more advanced tradecraft calling .NET methods, specifically really heavy usage of things like the system.reflection namespace to dynamically load and assembly memory. So here's an example of what that looks like with Metasploit. Way up top, that var syscode variable that you see there, essentially what that's doing is it's importing Windows DLLs into this application, specifically certain functions that it can use for process injection. So you'll see virtual alloc and create thread. Add type simply defines that .NET Core class inside of your PowerShell session that kind of allows you to call that. There's a shellcode variable. Then at the very bottom, you see those functions actually being called. So you see virtual alloc, which is allocating new memory. You see that copy function, which then taking your shellcode and putting it in that newly placed or newly created memory that has executable permissions. And then finally at the bottom, you see create thread, which is then running that shellcode in memory. This is an example of PowerShell in the wild. This literally was published like an hour ago when I was doing some prep for this talk, so I felt like it was a good example. So if you think some of these techniques are maybe dead with new modern EDRs and AMSI inspection, things like that, this payload was literally successful today. And we see some very similar things here, right? So there's a sleep at the top. It's adding some defender exclusions, which is super helpful that that's built into the system, right? Like you can just create your own AV exclusions if you have adequate permissions. And then finally, what you see here is this download data. What that's doing is it's pulling down code from a remote resource as a byte array. And then it's calling system reflection assembly to load those bytes into memory as an application. And then you'll see that method is equal to assembly.entryPoint, and then it's invoking that method. So it's a way of dynamically loading code into memory. You'll see red team frameworks like Cobalt Strike do stuff like this all of the time. And again, just to highlight that assembly load. So now we're going to transition a little bit to talk more about binary-based malware. So these are things like compiled code. And we're going to take a short break from code samples just to talk a little bit more about the theory, since it is fundamentally different. One of the key concepts you're going to want to understand is the difference between imports and exports. So imports are basically the DLLs and the functions that the application is pulling in that provides that additional functionality. If you have a sample that makes no attempt at obfuscating or hiding its true intent, the import address table will be a really good way of determining what functionality is contained in that sample. FireEye has a great tool out there called Kappa that you can run against deobfuscated binaries and get a good grasp of what they're capable of just based on imports alone. If you're dealing with something like a DLL is similar, but instead of having only imports, it exports functionality to other applications. So if you see any malware that's based in the DLL format or CPL, something like that, you're going to want to look at those exports and figure out which one of them is providing the additional functionality to another application. But the big thing with working with binary malware is realizing that Windows APIs truly do the heavy lifting. You don't necessarily need to understand all of the assembly and what it's doing all of the time. But if you focus on those core Windows API calls, you can work your way backwards to figure out what specifically they're doing. And there are certain patterns that you'll come to recognize over time that are really important. So for example, dynamic API resolution. Pulling in those DLLs and functions at runtime so you can kind of evade that static signatures and static detection. Other things like process injection, but just broadly think about the categories of malware that you're analyzing and what functionality you'd like it to have. So if you're analyzing an information stealer and you want to know, does this contain the functionality to steal data from the user's clipboard, you may need to understand how I would code that functionality in order to access the clipboard. Same thing with advanced stuff like EDR evasion. If you understand how you would code EDR unhooking, for example, it's easier to recognize that when you're analyzing a sample that performs that behavior. So let's take a look at some of those common patterns. So dynamic API resolution. So things that are going to be really common here are get module handle, load library, and get proc address. Those are those Windows API calls that are going to enable an adversary to pull in additional functionality at runtime to kind of evade some of those static-based signatures. Also process enumeration, basically listing through those different processes that are running on the system. They're going to use Windows API calls like create tool help 32 snapshot, kind of grab that snapshot of the running processes, process 32 first to grab the first item, and 32 next to kind of iterate through the different processes in that list to find either the processes that ransomware wants to kill, if it's something like a backup service or something like that, or potentially it's trying to find its injection part. Speaking of process injection, some of the patterns that you're going to really commonly see are things like virtual alloc, write process memory, virtual protect, and create thread. Now, there's a million different ways to perform process injection. This is probably the most trivial technique from over a decade ago, but the pattern is ultimately the same, right? An adversary needs to allocate a new section of memory. They need to write their shellcode to that section of memory, and then they need to adjust those memory protections so that section is actually executable because it's not by default. And then it needs to essentially start that function at that newly created address. Elastic has a really great blog out there that talks through some of the common techniques for process injection that will talk through those different Windows API calls more so than you'll see here. Additionally, malapi.io is a great source to start getting more familiar with this. And if you're reading or you're analyzing a piece of malware that calls an uncommon Windows API that you're not familiar with, MSDN will be extremely helpful, so the Microsoft Developer Network documentation, but also this website here, because it has a catalog of the different ways that adversaries have used that specific attack. So this is the most simple shellcode loader that most people will ever see written in C. Essentially, all you're really seeing is there is this payload that is written as a character array. And then inside of the main function, There's some casting and dereferencing and some magic stuff in C that's essentially treating that memory location as a function call. So then it simply calls that function in there. And this is what Metasploit's most simple shellcode loader looks like. A more advanced version of this comes from someone, 0xpat is what he goes by. I think he's a senior red teamer at Snowflake, but he has a great blog series about malware development. But here are some of the things that you're going to see. If we start reading it from top to bottom, looking for those things that we understand, we start to see those common patterns already, right? So we see virtual alloc, which immediately makes me think, okay, maybe there's some type of injection going on here, particularly because of this flag right here, page execute read write. It is extremely uncommon for a memory section to have readable, writable, and executable permissions. So that alone is a pretty big red flag. And then we see RTL copy memory. So this wasn't in our pattern that we discussed previously, but based on just reading that API name, we get a good grasp of what its capabilities are. It's literally just moving code from data from one location to another. And then finally at the bottom, or in the middle here, we see a little bit of a shift. The shellcode here just happens to be rot13 encoded. So each character just rotated 13 places to the right. So this is just a shift back. And then finally we see that create thread, which is then loading or running that code in memory. But what does this all look like in the real world? True malware reverse engineers are gluttons for punishment. It is a very complicated, complex task to truly reverse engineer an entire sample. But what this looks like in practice, you have to figure out the API hashing. So basically your malware family is going to find some dynamic way to pull in those Windows API calls. How are they doing that? Load up your type libraries. So before we saw that page execute read write on the virtual alloc, right? Well, once that gets compiled in computer language, that's the hex value 40. So how do you know that 40 corresponds to page execute read write? You load up your type libraries. That will automatically do that for you so your code is more readable. And then finally, then you do your string encoding. So you figure out, or you fix up your API names, sorry. So you figure out with all of those new loaded DLLs and libraries, like what do those function calls correspond to? You also have to do things like figuring out how your strings are encoded, because those will be used as parameters to those new API calls that have been resolved, and then writing signatures for it. So how do you detect this in your environment, either through a Yara signature or through something like threat hunting and figuring out how that parent-child relationship happens or what artifacts occur on disk. But figuring out the order of those things can be complicated. Sometimes it doesn't look as clean as this, and there are different dependencies for each one of those steps. But once you've finished up all of that, then you can actually start your analysis. Then you can start figuring out precisely what the sample is trying to do, because most samples in the wild aren't as trivial as the ones that we've discussed today. So just as a little bit of a recap, starting your analysis journey with heavily obfuscated and compiled code is just wrong. It leads to only pain and suffering, and it is absolutely the way that I started to reverse engineer. So this is born out of my lessons and my pain. But malware isn't magic. It's truly only special purpose software designed for like this really small, unique purpose out there in the world. But understanding how adversaries go about writing their code can help you understand the different design decisions that they make, which helps make you a better reverse engineer and malware analyst. But it's important to focus on your goal and not get sidetracked, not go down rabbit holes. Focus on only the code that you understand and work your way backwards from there. But finally, like, practice and have fun. Yeah, if it's not fun, you're not going to enjoy doing it, and it's not going to be something that you turn into a regular practice. So the key thing there is stay with it. Find samples that are fun for you. If it's too hard, try something else and come back to that harder sample later. So that's all I have for you today. I want to thank you all for your time and open the floor for any questions. It still works. It does raise a few detections now. It's definitely more common to see memory allocated first with readable, writable permissions, and then a call to virtual protect later to give it those executable permissions and remove the writable permission. That's definitely more common. But yeah, you still see RWX memory allocations out there. Awesome. Thank you all.